There we are. Great. So welcome to the last Zangwill Club of the year. As expected, we are online with Zoom, but I hope we will be able to offer Nico a warm physical welcome in Cambridge next year at one point. We'll see when. And it's a real pleasure to be able to have Nico's talk because we thought we were going to had to cancel, but we were all flexible and we were able to offer him this sort of weird slot of the mid December. Despite that, clearly people are still coming in, and we are going to be recording the talk, so it will be available for posterity. So welcome, and I'll give the power of the word to Sarah Jane Blakemore, who will introduce.
Hello, welcome to this talk, and after the talk, as you know, there'll be a Q&A, so please think about what questions you might like to answer, and you're welcome to either ask, you're welcome to either ask them verbally or in the chat function. That's fine too, and you can do that at any point during the talk. Okay, so it's my pleasure to welcome Nikolaus Steinbeis to give this Zangwill lecture. Nico is an associate professor at UCL. He actually did his first degree at UCL. Am I right in remembering?
Yeah, that's correct, yeah.
And then a PhD in Leipzig. And I think you did your PhD on a slightly different topic of music in the brain. And then he went to Zurich to work with Tanja Singer and Ernst Fehr. And then he came back to UCL as an associate professor. He does really exciting research on neurocognitive development in childhood in humans. And he has all sorts of really impressive and prestigious honors and awards. He's he has an ERC fellowship. He's currently an ERC independent fellow, and also a Jacobs research fellowship. And various other research grants, which enable him to do this fascinating research. So we're really pleased that you could rearrange your talk after being unwell a couple of weeks ago, and we really look forward to hearing about your research today.
All right, thank you so much, Tristan, and thank you so much, Sarah Jane, for the invitation and the really kind introduction. It's a real pleasure and honor to present in the Zangwill Club today, and thank you also for the flexibility. So I'm going to just make this smaller. So today's talk, the title I've given it is Old Wine in New Skins, a fresh look at cognitive control development, and it reflects some of the most recent work that we've done in the lab over the last 2-3 years while I've been at UCL. Most of the work, in fact, pretty much all of the work that I'm going to present has not been published or is in the process. We've submitted most of it. And even though Sarah Jane mentioned that my focus is on neurocognitive development, there's not a lot of neural data that I'll be presenting today, but I don't think that necessarily matters in terms of sort of the theories that we're going to allows us this to discuss. So I'm just going to break down what the sort of core focus of my research outfit is at UCL, which is called the Developmental Change and Plasticity Lab. So the kind of theoretical questions that we tackle are relatively broad. In terms of developmental change, what we're really interested in is how developmental change unfolds, whether it's quantitative or qualitative, whether it's gradual or sudden, or whether there's sort of any discontinuities across age in any particular phenotype that we're interested in. And in terms of plasticity, the kind of core issues we care most about relate to sensitive periods and sort of a transfer or generalizability of environmental experience onto other domains. So that's the sort of broad outline in terms of themes and topics that we care about. And the kind of phenotypes that we've applied this to most in the past have pertained to social abilities, like emotional egocentricity, or being able to overcome one's own emotional state to accurately predict and say how someone else feels. as well as theory of mind or mental state attribution, as well as pro-social behaviors, such as sharing with others or helping others. So those have been the core topics that we've applied sort of most of our techniques to in terms of understanding how they change and develop. And one really striking finding has been that most of the developmental change that we see in these relatively distinct social phenomena can be explained by co-developing abilities in cognitive control. So cognitive control has really been able to account for a lot of the age-related variants that we see in developmental change in these social abilities and pro-social behaviors. So cognitive control has sort of appeared, as it were, as a particular phenomenal construct of interest, which we now study in much more detail. I didn't set out to be particularly fascinated by cognitive control, but this has just sort of emerged, I think, from the data and the types of questions that we've asked in the past. So just going to give a very brief and broad definition of cognitive control, which in my view relates first and foremost to an ability that serves us in striving for particular goals. So all of us have goals every day and all day, really. These might vary radically between people, but sort of also within ourselves, there's a lot of intra-individual variance in terms of what goals we have at any given point in time. It might be weight, it might be climb a tall mountain, it might be publishing in Nature, it might be all three of those, in fact. And to be able to achieve those goals, we need to keep those goals in mind and resist temptation on the way. So the broad definition then is that cognitive control supports flexible and adaptive responses to environmental changes in pursuit of goals. And just a primer, I think this notion of goals and this motivational component, I think, is absolutely core to our understanding of cognitive control and to our understanding of how cognitive control develops. So it's been shown, I think one question is, why would we care about cognitive control in the first place? I think the reason why we should care about cognitive control is that it's been shown to be very, very important for a range of other domains and real life outcomes. So in children, having sort of good and stable cognitive control is predictive of the quality of their social relationships, how well they do at school, their subjective well-being, as well as mental and physical health. And even more importantly, childhood cognitive control is highly predictive of these later life outcomes, such as social relationships and mental and physical health. So it's really something that's sort of at the very core of daily functioning, and that translates to a range of different domains. Now, in terms of cognitive control development, I'm going to just briefly introduce you to sort of a canonical view, a traditional view that's been very, very prevalent in how this has been studied, and is sort of very much supported by data of brain development. So what's typically reported or said about cognitive control development is that this develops significantly throughout childhood and adolescence and into adulthood, and these developments occur because of cortical maturation. So the kind of framework that that this sort of predicates is that we have particular brain regions that are involved in executing a particular cognitive control task. So in this case, these are brain areas that are activated while carrying out the stop signal task when participants are stopping versus when they're going. And what we see is strong and heavy involvement of dorsal and ventrolateral prefrontal cortices. And what we know about brain development is that especially prefrontal cortex develops late. So what we have here is, this is a paper by Gopte and Guide from 2004, but it's very, very commonly shown, especially in the context of these types of studies, is sort of a timeline of cortical thinning. And we see that dorsal and ventrolateral prefrontal cortices are among the latest to mature. So the idea is then that the kind of brain regions that are required to perform cognitive control tasks, or that allow or enable cognitive control, are late developing. And here's just sort of a few examples of this is interpreted. I'm going to read those out. So the first one is developmental improvements in inhibitory control may be supported by age-related enhancements in top-down effective connectivity. The second one is greater magnitude of activation in a young group compared with an adult group is interpreted as limitations in the neural components supporting activation in a region that may not have reached efficient mature levels. And the last one, which has actually taken a paper that I co-authored together with Evelina Kroner, is ever since the discovery that patients with damage to the PFC show deficits in cognitive control, theoretical models have suggested that cognitive control development is closely tied to PFC development / maturation. And I think the implicit notion in this kind of a perspective is that there's actually a bit of an inverse lesion model of child development. So what we have here is a schematic depiction of that iron bar, which poor Phineas Gage had, the accident that he was involved in, and that children are really sort of seen as lesion patients, where the prefrontal cortex is not fully engaged, and therefore they can't perform all these cognitive control tasks. And that brain maturation results in a change in competencies. Now, I think that there are some people who don't believe this, but I think this is a very common assumption. And I think even if you speak to researchers directly, not many would necessarily endorse this explicitly, but these are some of the assumptions that kind of creep through in much of the literature. And I think these examples that I've been guilty of myself make this quite clear, as it were. And I think this is problematic. I think this is problematic for several reasons. The first being that there's a constant debate in developmental psychology between performance versus competence. So performance on any given task versus whether that actually indicates that someone is truly competent in being able to perform this task. And I'm just going to give a couple of examples. So theory of mind, this has been commonly studied ever since Dennett proposed this by what's called a false belief task. So Perner and Wimmer introduced this in 1983, and ever since then this is sort of taken as the classic example. If you pass a false belief test, an explicit false belief test, where young children are given a particular scenario and then asked a question where a protagonist is going to look for a ball, this is commonly passed between 3 to 4 years of age, and this is relatively invariant. And then in 2005, it was shown that when we strip away all these sort of extraneous variables, language, inhibition, then actually what we see is that sort of using non-verbal tasks, that even 15-month-old infants are able to pass this. And in some cases, even 9 or 10-month-old infants. And, I think that there's much debate over what this actually means, but it does suggest that sort of an incredible amount of flexibility actually in terms of what these core competencies are. I'm just going to give another example, which is on cognitive control development, particularly on perseveration and the A-not-B task. So the A-not-B task it's a classic example of how cognitive control is tested, and in these scenarios, infants are present, the experimenter, there are 2 locations and an object is repeatedly hidden under one location, and then it's hidden under another location. And the test is, where does the infant look for this? What's the kind of prediction that they make? And most often they will wrongly predict that the object has been hidden under the same location as on many previous trials. And there's a very interesting paper that was published by Topal from the group of Gerge in Hungary, where they argue that the kind of communication, the kind of non-verbal communication of engaging in eye contact with the infant and referring to where the object is going to be hidden, what they call ostensive communicative cues, lead to the infant adopting a kind of pedagogical stance where they suddenly infer that this is very generalizable in terms of what they do. So what they did in a control condition is they started hiding these objects, but in this particular context, they didn't give any communicative cues. And what they see is that, so this is proportion of correct searches. And what you see is that on the B trials, in sort of the normal context, there are many more errors than on the A trials. But in the non-communicative context, all of a sudden, this is massively boosted. So it just suggests that, even relatively stable and very common markers of cognitive control, there appears to be much better performance, as it were, when some of these sort of task-specific potential confounds end up being removed. I think another line of evidence which sort of questions this whole sort of maturation competency framework comes from neuroscience itself, and this has also been debated for a long, long time, where we know, for instance, that neural changes continue long after cognitive changes have actually taken place. I mean, sort of the whole literature on both theory of mind and cognitive control. I mean, theory of mind sort of supposedly draws on late developing brain regions, but it seems to be able to, 3-4-year-old children seem to be able to pass it, but those brain regions continue long after it. So what exactly does that mean then? So what I would argue is that the sort of competence maturation account actually underestimates children, because it seems to make it a lot more fixed than it actually is, and it also misrepresents the underlying abilities. And most importantly, it fails to capture the sort of dynamic and context-dependent nature with which cognitive processes take place. And what I would like to argue for, and I'm going to, most of the data, the studies that I'm going to present will speak to this, is that development needs to be seen much more as a dynamic and adaptive, ecology-dependent process. So there have been a few, few recent studies that have suggested this in terms of the kind of strategies that happen, especially around cognitive control. And what I'm going to be focusing on most is these motivational processes. So that cognitive control is a goal-driven process, and that we really need to understand how these goals actually change in development to be able to say more about how cognitive control develops. So this talk is on the dynamics of cognitive control development, and in the first set of studies, I'll be presenting one study on effort-based decision-making and 2 studies on reward-based decision-making and cognitive control, obviously, each time. And the second set of studies will be on the plasticity of cognitive control, in particular looking at an intervention study that we've recently started carrying out. So I'll just deepen this discussion then on the link and relationship between cognitive control and goal pursuit, and why or how this would actually be so important. So as I've argued before, and so have many others, cognitive control is deployed specifically to attain goals. And as a result, it is highly sensitive to the associated costs and benefits. So what happens is that there's sort of a relatively stringent cost-benefit analysis that's being made in terms of the effort that's required to pursue a particular goal, and the goal is going to lead to associated rewards. So the reason why cognitive control is believed to be costly is because there are intrinsic processing costs due to sort of information processing limits. There are limits to, for instance, our working memory span. And that as a result, there, opportunity costs arise. Whatever information I hold in mind right now precludes my ability to think about something else. Whatever I'm attending to now means I won't be able to attend to something else. So there's a sort of a whole bulk of literature showing that cognitive effort, much like physical effort, is aversive. I think the bottom line is, we sort of like to have it easy. We're somewhat lazy. I don't think that's, I'm speaking a relatively new truth here, but this has been picked up by the experimental literature as well. And that there's an important function to this sort of subjective experience of effort, because what it's meant to do is it sort of forces us to prioritize our resources in the context of the goals that we would like to achieve. So what's known is that goals can offset these costs. So rewards have been shown to improve cognitive control performance, and this seems to be somewhat invariant over age. But what we don't know, and this is going to be a point that I'd really appreciate a proper discussion, is that we don't really know how goals actually change over development. We have, I think, decent leverage in terms of what we can do in the context of any given task, that we can make things more effortful by making tasks more difficult, and we can introduce rewards, and the kind of reward that we introduce is usually money. So, we have a chance to operationalize it, but in terms of actually making this real, we're still quite far off, and I'm going to discuss those ramifications towards the end. So the first study is on effort-based decision-making. Here's just a little bit of background then. So effort-based decision-making is usually studied either using implicit task choice paradigms or explicit discounting paradigms. I'm just going to introduce those briefly because that'll shorten the time it takes me to describe the paradigm that we ended up using. So this is the first kind of paradigm that was used by Walter Kuhl in 2013, co-author is Matt Botvinnik, where participants are shown 2 decks of cards, and what they need to do is they pick a deck, and on that deck, once they pick the deck, they're shown a card, and that card displays a number, and the number is either blue or red, and depending on whether it's blue, I think they need to say if it's odd or even, and if it's red, they need to say if it's higher or lower than 5. And unbeknownst to the participant, each deck is associated with a different number of task switches. So let's say the green deck, for instance, has 10% of task switches, so switches of the color of the number, and the orange is associated with 90% of task switches. So participants aren't told this, it's implicit. And then what's of interest is how many times or how often participants choose the low demand deck versus the high demand deck. And this is what you see then here over trials. These poor participants had to perform this 500 trials, and what you see is sort of a gradual tendency towards choosing the low demand deck. They also show that demand avoidance, so avoiding the high demand option, is correlated with independent indicators of self-control. So this is just sort of a classic paradigm of the implicit task, and in an explicit context, it's a very common discounting task. So participants are given the experience of a task that varies in how effortful it is. So here's an n back task, and obviously 1, 2, 3 back, depending on what it is, it's going to be more effortful, and then they're given a choice of a low reward for a low effort and a high reward for a high effort task. And what we see is, and just in terms of the data or the sort of the developmental pattern, in the implicit task choice paradigm, we see a gradual shift. So younger children, 6 to 7 year olds, seem to not, their choices are not affected by how demanding those different decks are. And this changes with age. So adults sort of demonstrate a much clearer preference for the low demand, which emerges with time. So this is in the context of an implicit task, and in the context of an explicit task, we see that children between the ages of 6 to 12 years, they discount effort. So sort of more increased rewards are required for one to engage in something effortful. And this is invariant for that age group. So whereas with implicit choices, this seems to emerge with adulthood. In explicit choices, younger children are able to do this already when they're sort of asked explicitly about this. So what we did in our study is we combined an implicit and an explicit measure in one paradigm, and we also tried to get a better resolution of effort. So an n-back task is not necessarily that suited. So what we did is we gave children a rapid serial presentation task. And what we see here is this is Woody the owl, and they need to help Woody the owl find wands. And each time they see the owl pointing towards either of the 2 sides, they need to switch attention effectively in terms of where the wand is presented. So they're meant to fixate centrally, and the wand is presented either side. What happens is that each trial has 40 presentations, and there is an exposure of different number of switches. So it'll either be one switch in those 40 presentations or 6 switches in those presentations. And what we then have is an implicit and an explicit task, which is based on this. So the children have 30 choices between 2 of these whiches. One is associated with low effort and the other is associated with high effort. And there's also an effort discounting paradigm, where here is the level of effort is explicitly represented, and here's the number of rewards that they can offset with this. And we looked at this in 84 children between the ages of 6 to 11. And what we see quite nicely, so here you have the number of attentional switches on the x-axis. What we see quite nicely is that performance doesn't change as a function of attentional switches, but the perceived effort does. So the more switches participants experience, the more effortful they experience that particular task. And this is, again, age invariant. All children between the ages of 6 to 11 perceive this, or rather this did not interact with age. And when we look at their decision making, so what we see here is the sort of gradient of implicit to explicit. The children in our task didn't differentiate between low effort and high effort trials on the implicit task. When we asked children, okay, so which one of these 2 do you prefer? We see an interesting age-related switch in that younger children seem to prefer the high effort option and older children seem to prefer the low effort option. So there's some interesting age-related variance here. And when we ask them explicitly in the discounting paradigm, we don't see any age changes, and all children discount equally, as it were. So it seems then that cognitive control is modulated, or rather that children are sensitive to effort, and that they use these effort computations to guide whether they engage in a cognitively demanding task or not. And there are some interesting age-related interactions in terms of how explicit those effort representations need to be made for children for whether they do or whether they don't. So the second task, or the second study which I want to talk about, looks at cognitive control in the context of value-based decision-making. And there's a lot of literature on value-based decision-making, perhaps a little bit less so in the context of development, which has studied this by wanting to understand, sort of how we navigate our world successfully, and how we can sort of increase our sort of utility or maximize rewards in the context of how we navigate the world, which is really by learning about our actions and the extent to which our actions can lead to rewards or not. And there's a huge amount of literature on sort of reinforcement learning and value-based decision-making that posit a so-called just sort of a dual systems account of how this takes place. So on the one hand, it's argued that there is a model-free system which guides sort of relatively basic reinforcement learning, where we simply repeat actions that have previously led to a reward. And on the other hand, it's argued that there is a so-called model-based system, which is goal-directed, and it takes into account the sort of broader environmental structure and allows us to generalize and make inferences about the kind of actions that we should take. Now, typically, humans display both types of learning. And linking this with cognitive control can be done in 2 interesting ways. So model-based, the definition that we give here, model-based decision-making, is analogous to cognitive control in that it reflects the representation of internally maintained goals to overcome habitual actions. And on the other, it's a really interesting question of how we actually arbitrate between these 2 different systems to produce optimal outcomes, because presumably the cost of engaging in model-free versus model-based decision-making is different. And the question is, how do we actually arbitrate or sort of offset these costs depending on the kind of situations that we find ourselves in? Now, the previous work that's been done on model-based decision-making has used this task. It's called a two-step task, where participants are shown two abstract symbols and they have to choose between them. And depending on which of those they choose, they get taken to a next state that probabilistically takes them to, again, one of two options, either 70% to option A or 30% to option B. And these other options, or sort of at the second stage, they are associated with a reward, and that the probability of that reward changes over the number of trials. And this kind of a task allows one to dissociate between model-free and model-based learning. So I'm just going to go through what those sort of patterns of results would look like. So what's most interesting in the context of these tasks is the stay probability of choosing, of which one chooses at the first stage. And the question is, what happens when a previous trial has been rewarding or not? And somebody who is perfectly model-free, so who's just sort of entirely driven by reinforcement learning, they will simply repeat an action that has been previously rewarding, and they won't take into account whether the transition before was common or rare. That's not going to have an impact. Somebody who's model-based is going to take that into account. So they will repeat a previously rewarding more often if it is a common transition, and they will switch more often if the previous choice did not lead to a reward. Now, what we typically see in the data is a mixture of the two. So as I said, typically humans display both types of learning. So we see a very nice sort of differential contributions of model-free and model-based decision-making. Now, again, coming back to that link with cognitive control, it's been shown that this sort of an index of model-based decision-making correlates with an independent marker of cognitive control. So it appears that cognitive control plays an important role in model-based decision-making. And developmentally, there's so far only been two studies that have looked at this. Developmentally, it's been shown that children between the ages of 8 to 12 do not actually show any contributions of model-based decision-making to their behavior at all. And this is something that appears to emerge only in adolescence. So here, if we look at the interaction effect of reward by transition, this gradually increases with age. Now, the study, the paradigm that's previously been used had a few design flaws which might not have lent itself as well to study this in developmental populations. So firstly, it was very, very complex. It's quite difficult to understand. And the fact that the transitions were probabilistic made it quite difficult for younger children. I think the suggestion is that the task is so complex that younger children, they were sort of what's the word? Stopped from being able to exploit the fact that model-based decision-making actually would be helpful. That we came up with a task which was simpler to understand. It was deterministic, and more importantly, where model-based decisions actually yielded more rewards. So something that was previously was overlooked is that model-based and model-free decision led to the same number of rewards, which meant that anyone who would be doing that computation of whether it's worth engaging in something cognitively effortful would have presumably taken the cheaper option, which is to be model-free. So this is something that we changed in the context of the new task. And we also looked at how model-based decision-making might change as a function of whether you're in a context that is highly rewarding or not. And we looked at this in 118 children of a similar age range that were between the ages of 6 to 11 years. And we also studied this in 24 adults. The adult data isn't that interesting because this has been done before in adults. So this is more just sort of as a replication sample, as it were. Now, what we see, so this is the extent of a model-based decision-making. We've got a parameter from our computational modeling, which is called W. what we see is quite a lot of variance in our children, but when we compare the children overall to simulations, which sort of estimate that, if you just simulate the data, a W of 0.25, which isn't 0, children are significantly different from those random simulations, which suggests that, in spite of previous research, children do show evidence of model-based decision-making in their behavior. When we look at whether there's a stakes effect, so when children find themselves in a situation where there's lots or little at stake, we don't see a significant difference between those two conditions. So it appears to be, sort of overall, children don't seem to be sensitive to whether lots or little is at stake. We managed to replicate a stakes effect in adults. So adults show greater or more contributions from the computationally effortful decision-making strategy when there's more to gain. And then when we look at children, when we split children up and we look at sort of what happens within this large age range that we've got of 6 to 11 years, we actually show that whereas decision-making for low stakes remains relatively stable, there's a significant age-related increase in model-based decision-making for high stakes. And this suggests that, sort of on the first hand, that, children do show indicators of model-based decision-making overall, and that this is adaptively titrated or modified depending on how much is at stake. And this just sort of suggests more broadly that these indicators, these value-based indicators of cognitive control, are modulated depending on the goals that are at stake. Now, the third study in the context of these sort of dynamics of cognitive control development relates to how value and different rewards might be valued and impact cognitive control differently across development. And the reason this is interesting is, because I don't think we necessarily think enough about how exactly we operationalize rewards and goals in the context of development. So this is something that we wanted to take a closer look at. The reason why we did that is because developmental studies on value-based decision-making, and the one that I just presented is another example, they typically assume that rewards have the same meaning for different populations. And that's sort of quite nice in a way, because, sort of by doing that, it allows us to use, literally the same paradigm. And there might be some tweaks around how the rewards are introduced. It makes no sense to tell a child that they can win £100, but overall, there's a basic sort of a tacit understanding that this is a common metric that one can rely on. But I actually think that there are very good reasons to think that how money is valued is very likely to change a lot throughout development. So we can think of reasons that it could increase due to its acquired value. Somebody, an adult knows what they can do with money, whereas a 6 or a 7-year-old, they have much less experience in terms of what money can buy. It could also decrease due to familiarity, or the novelty effect of having money could be much more exciting for children than for adults. So I think there are several reasons that make differential predictions, at least, for why money would not necessarily be identical for different ages. And I think this is important because the kind of effects that we see in the context of value-based decision-making tasks are always taken at face value. So, for instance, steeper discounting in children compared to adults is always meant to indicate impatience. But it may be that in the context of those particular paradigms, children are just the monetary reward is just worth a lot more for the children, which is why they would want it sooner than the adults. So I think I think this just sort of requires us to take a step back and really think about, okay, how do we actually introduce these rewards to be able to look at how rewards impact decision-making, but also cognitive control. So yeah, like I said, this has implication for a host of domains, decision-making and cognitive control. Now, so in the study that I'm going to present to you now is we actually contrast these secondary rewards money with the effects of primary rewards, such as pleasant tastes and smells. And the idea is that primary rewards would be less affected, as it were. So there's good evidence that the capacity for sensing postnatal flavors begins in utero, and the systems are functionally mature and adult-like by the end of gestation. Now, that's not to say that there's not sort of significant development in olfactory and gustatory cortices, but more seems to be in place to appreciate the effective significance of primary rewards compared to secondary rewards. Here's some anecdotal evidence. These are my two children. What you see here is, my daughter tucking into a muffin. My son's already finished his. I think anyone with, sort of who's around kids and able to see kids, they'll be able to see just sort of what the massive effect is of, say, anything sweet or pleasant tasting. So what we did in this study then was we investigated how the value of a primary reward like juice and a secondary reward changes across development and how this might impact cognitive control differentially. So the way we looked at this, we compared the valuation of primary and secondary rewards, and we studied 22 children with a mean age of 9.5 and adults with a mean age of 24.5. And we introduced the two rewards. The juice was introduced where they got to sample one of 3 juices and they got to pick their favorite out of 3. And the money, adults were paid out with a real currency and children were paid out in a lab currency to exchange for a toy. And that was to sort of keep the agency constant. It was quite important that children knew that this was their money that they could spend as opposed to that the adults might pocket. And we gave 3 paradigms. One was a subjective evaluation of the rewards. Another was the willingness to work for a reward. So, in the animal literature, we have some really, some very neat paradigms where the best indicator of how valuable something is to measure how willing someone is to engage in something effortful. Now, typically we use physical effort. We didn't have the chance to look at physical effort, so we looked at cognitive effort. And the idea was just to allow us testing for how much cognitive effort our participants would go through to obtain either of those 2 rewards. And then we also looked at the effect of these 2 different reward types on cognitive control. And the sort of tentative hypothesis, but non-directed, was that we would see developmental changes in how monetary rewards are processed. So here's just a quick description of the paradigm and the explicit evaluation. They were shown either of the 2 rewards, and participants had to indicate how much they would like to receive this reward. In the willingness to work paradigm, what we did was we gave our participants an SPM raven before they started the experiment. And, and they got however far they did. And then afterwards, so, obviously with the SPM raven, it gets progressively harder and, adults get further than children do. And afterwards, we told our participants for this particular task that they would be able to do the SPM raven again. We would give them 1 trial of the raven, and that SPM raven would differ in terms of difficulties. It'd either be easy or medium easy, medium hard, or very hard. And what was nice about this is that it was perfectly anchored with how easy or hard children found it versus adults. So this was sort of perfectly within individual differences. And here was, this is just sort of how a trial was portrayed. They could choose whether they would be willing to work on an easy SPM raven for coins, as it were. And that allowed us to sort of get a measure of how willing they are to work for either of those 2 rewards. And we obviously modified this depending on which reward was at stake. And finally, we gave them a cognitive control task. So this was a flanker task, and during the flanker task, they either received money or juice, and we were interested in looking at how well they do in the context of this task, and how these 2 reward types, whether they have an invigorating effect or not. So here's the data then from the explicit valuation paradigm. Here we have the adults and here are the children. This is the primary reward, so that's the juice. And on the right side in each panel is the secondary reward, that's the money. And what we see is that overall, they're sort of relatively comparable between adults and children, but adults seem to care more about money than they do about juice when explicitly asked about this. Here's the data from the willingness to work paradigm. Now, what's portrayed on the y-axis is the extent of discounting and how willing they are to work for it. And what we see again is some good constants between adults and children, but that adults are willing to work more. So this is sort of inverse the y-axis, but adults are willing to work more for a secondary award than for a primary award, whereas for children this appears to be quite constant. And when we look at how what the invigorating effect of money is on cognitive control for children and adults, what we see is, so here's a probability of a hit zone, so an accurate response. We see that money has a more invigorating effect than juice does for the adults, but for children this is relatively constant. And we also show some relatively nice associations where the performance in the cognitive control task is directly related to how much adults value this in the subjective valuation task. So here's just an interim summary then from the first part, which is that children's deployment of cognitive control appears to be sensitive to effort, sensitive to reward, and sensitive to type of reward. And that suggests that cognitive control is a fundamentally dynamic and context or goal dependent process. And the development in cognitive control seems to be primarily then about the development of its dynamic use across a range of different contexts. Now, sadly, we know very little about ecological goal development, and I think that poses a problem somehow. And what I'd like to suggest, or I think propose, is that we need to see a shift in how goal development is studied. But I would advocate that, in addition to the kind of experiments that we are currently running, that we include experiments that sort of embrace the fundamentally different nature of different age groups and what they would care about. And that is actually very, very key in terms of understanding how these processes that underpin goal processing and goal achievement, like cognitive control, can be much more clearly understood. So the second part of the talk is on another extensive part of our research agenda, which is on the plasticity of cognitive control. So I'm just going to introduce a little bit of background and then quickly move on to some of the studies that we've done in our lab. Like, as I've said before, it's an important question, I believe, because cognitive control or executive functions seem to be very important for later life well-being. Now, in the context of plasticity, what I'm referring to is really training cognitive control, training executive functions. Most of the work has focused on training working memory, and there's not an awful lot on other domains, like inhibition, for instance. And the evidence overall appears to be quite mixed. So, the kind of randomized control trials that compare a particular form of executive functional cognitive control training and active controls, the evidence is, it's mixed. And this is sort of shown in the individual studies as well as in the meta-analyses that are coming out. And this is somewhat baffling because, or not baffling necessarily, but so the basic rationale here is that we have an executive function like working memory, and this appears to be related to a high order construct like maths or reading ability or IQ. And the idea is then, okay, if we try and improve this, then we really ought to see improvements on these associated functions, but we don't see that very often. We don't see that at all, especially not in the context of what's known as far transfer. So this would be considered far transfer because the two functions are relatively distinct from one another, and the evidence for far transfer is slim. And as I said, I do think this is baffling, and I think others think this is baffling too, because we know that experiences do generalize in long-lasting ways in natural learning contexts, and we also know that the executive functions can be persistently affected by negative events. So the question is really, what are we getting wrong in the context of these types of training paradigms? So with the kind of study that we're doing, we try to overcome this to a certain extent, not entirely, but to a certain extent. And the question we ask is whether we can train cognitive control, whether we see transfer, and whether, if we do see transfer, whether this is durable. Now, one feature that I like about training studies is that it doesn't just give you a handle on plasticity in general, but it also allows you to say something more general about the kinds of mechanisms that are involved in the context of particular functions. So it allows us to address particular questions about what training can tell us about cognitive control. And one of these questions lies very much at the core of how cognitive control is understood. And that is whether cognitive control is primarily a process of inhibition, or whether in fact it is more about something like being able to monitor one's environment. So there's just in the literature, there's been a really dominant view that inhibition is the core process of cognitive control. It's really all about stopping. What we have here is a stop signal task to illustrate this. So here we have go trials and we have stop trials, and it's what's shown is that stop processes are seem to be critically subserved by right inferior frontal gyrus. And in 2012, a sort of novel proposal was made by Chatham from the lab of Yuka Munakata that argues that inhibition could be more or entirely about monitoring. So it's more that going and stopping are about being able to select the right action, as it were. And what they show is that in this particular context, for instance, when the participants are instructed not to stop on stop trials, but to respond differently than on go trials, in fact, respond twice, then they demonstrate that there are virtually indistinguishable behavioral, psychophysiological, and neural signatures. And that suggests that it might be that cognitive control isn't really about inhibition at all, but it's more about a broader process of being able to monitor one's environment and being able to select the right action. And training studies offer a really interesting and good window into the causal relationship of inhibition and context monitoring to cognitive control. So what the data would look like to be able to speak for either of these two hypotheses when we run a training of cognitive control is that either the effects of an inhibition training and a monitoring training are identical on cognitive control, and that would suggest that it might be the same process, or in fact, if it's different, we would see a difference also in the training outcomes. And that's exactly what we looked at in the context of a training study. So in the training study, participants, it was effectively we used a stop signal task where they were presented with cues, stop and go cues, and occasionally a stop cue was presented. And what is nice is that the stop signal delay waxes and wanes perfectly with the performance of participants. So it actually lends itself very, very nicely to studying training cognitive control. And we embedded this in the context of a gamified and variable, highly adaptive, complex and diverse training regime. So our participants' children were told that they had a plane and they crashed that plane in the desert, and they had to find the sage to get spare parts. to fix the plane and fly back home. And to get to the stage, they had to navigate these different worlds, and in the context of these worlds, they had to perform different tasks to obtain coins and gems that they could give to the sage. Otherwise, he would give them the spare parts. And let me see. Does this play? Yep, it does play. So this is just a demonstration. So, one navigates through these different worlds. Sorry, this is actually quite slow, not the best video. And within those worlds, one can choose, here's a set of instructions. And okay, and this is sort of a very, very basic kind of training paradigm. And yep, okay, there you go. These are 3 stop trials, and now is the inhibition trial, exactly. So that was the basic idea, and we gave our children multiple permutations, and this sort of got more variable and complex. And we had 3 training groups that were maximally adaptive. So we had an inhibition group that either responded to a go signal and had to inhibit to a stop signal. We had a context monitoring group that responded to the go signal and responded twice to a stop signal. So in this context, they would see the rock and the gem, and rather than not pressing, they had to press twice. And we had a response speed group that all they did was, regardless of what was shown, they just had to press as fast as they could. And what's important is the training was adaptive in each case. So it got harder and easier depending on how well they did. And we gave a pre and a post test looking at both inhibition in the context of the stop signal task and reactive and proactive cognitive control in the context of an AXCPT task. So we looked at this in 60 children between the ages of 6 to 10. And like I said, we had 3 training groups. The training lasted for 6 weeks. We got 1 session at school and 3 recommended sessions at home. And there was a pre-post test at school, which lasted for 1 hour each. Now, we looked at the number of training sessions they did and the motivation. Number of training sessions did not differ between the groups, and the motivation was also comparable between the 3 groups. So now we just look at the training data. So how did their performance in the context of these games change over the course of the training? And what we see here is in the top panel, a measure of the SSRT, and in the bottom panel, it's broken up for the participants. And we see there's actually quite a lot of variance. So, the slopes are quite different between our participants. So some improve very rapidly, very quickly, others don't improve at all. But overall, it seems to be that SSRT performance improves as a function of their inhibition training. Now, in the monitoring group, what we looked at is how fast they responded on the double press. We see something quite similar, a significant decrease as a function of the training. And in the response speed training, it was much the same. We saw a significant decrease as a function of the training. So this was, sort of reassuring to us that the 3 trainings seem to have been effective. The question is now whether this has any impact on our measures of cognitive control, and whether there is a significant difference in the inhibition and in the monitoring group. So first, I'm going to show you the data from the stop signal task, which was given pre-post. And what we see is a significant difference from pre to post only in the inhibition group. And this was when we look at the SSRT and when we look at the stop signal delay. So inhibition training only translates, as it were, to the SSRT in a pre-post measure. Now, we were also interested whether this transfers, and transfer in this case is quite loosely used because it was still an executive function or cognitive control task, namely the AXCPT task. The AXCPT task gives us really sort of good measures of proactive and reactive control. So there's a difference in the cognitive control literature. Proactive control is sort of our ability to upload task demands and prepare for upcoming events where control is needed, whereas reactive control is we're responding to the situation as needed. And proactive control in the context of this task is indexed by an improved performance of one trial type over another trial type. So we looked at how this index of proactive control changed as a function of the training. And when we look at this proactive control score, we see that this improves only in the inhibition group, significantly at least. And there's no significant difference in the context monitoring group, and also not in the response speed group. And to us, this suggested that when we use such a training paradigm to really understand the core mechanism of cognitive control, inhibition does seem to be most crucial in the context of child development, which is why we focused on this in the context of a much larger intervention study. So this is what we're currently embarking on, that asks the question whether we can train cognitive control with transfer to other domains with durable effects. Now, Sarah Jane mentioned it already. This has been kindly funded by the ERC. And the idea here was that we'd sort of have a sort of large behavioral test battery and look at brain structure and brain function before the training. We'd give an 8-week training, and we'd look at brain and behavior again after the training and have a 1-year follow-up. And the original plan was to do this with 300 children, typically developing, recruited from London, London or Greater London, and then this happened. So it somehow ground to a halt, and we had to shift our strategy quite significantly. So what we now have is it's actually not too bad at all. I'm relieved that sort of in terms of the careers of my PhDs and postdocs, there's enough for them to get on with, and we're just exploring that data. But we have a significant portion of the data before and after the training. One thing that we obviously couldn't do in the 1-year follow-up is we can't take any brain scans, but we've got behavioral data. So we switched very quickly to online testing, and that was fortunately very effective, and we had a decent enough uptake from the parents. So the kind of transfer domains are really extensive, and again, so, what I have here is sort of in shades, as it were. What goes from near to far transfer. We look at a range of different executive function tests from the SSRT, which is obviously most closely related to our training, to cognitive flexibility and working memory. We look at IQ, different decision-making tasks, creativity, mental health and well-being, as well as more broadly, metacognitive abilities and willingness to expend cognitive effort. And I think, so we're in the process of analyzing these data, but, obviously we're thinking ahead just in terms of the kinds of questions that we can address with our data. So the approach that we like to take is that rather than looking just at individual tasks and how any individual tasks change as a function of training, that we rather look at underlying latent factors. So we just sort of see how performance on these different tasks hangs together and how this might change. Trying to understand individual differences. I think this is quite an overlooked feature actually in the context of this intervention literature, is whether and how some might respond better to the training, and we've sort of got enough data to actually construct interesting profiles, as it were. We can get a better handle on the dynamics of the training process. So, sort of 8 weeks of training, if they've done it with the recommended number of sessions, then that gives us 32 data points per individual, which is, that's a staggering amount of data, which will give us a really nice handle on the fluctuations of training-related performance during those 8 weeks, and obviously an attempt to try and integrate across these different levels of analyses, so from brain and behavior, having that longitudinal approach as well as an intervention. So the kind of sort of targeted pre-registered questions that we can answer with this, sort of one is, that's just an example, how does training cognitive control impact frontostriatal connectivity and in turn cognitive control? One question that we were interested in from the outset, but we weren't quite sure how to address, but where, so it might have been a silver lining of COVID, is the question of how training cognitive control could buffer against the negative impact of a stressor. So far, with the exception of a few longitudinal studies, there's not an awful lot of causal evidence that this cognitive process, which appears to be really important for well-being and mental health, is actually relevant. So what we did was, when COVID struck, we had enough participants that had already done the training. We had some participants that was already doing the training. And so we asked, we gave them questionnaires on their well-being, or rather the parents, and we can see what the effect of the potential buffering effect of training cognitive control might be in response to the negative impact of a stressor. We can look at how wide transfer is. So given the different domains that we look at, we can look at how wide transfer is. We can also study whether there are age-related changes in training effects, and whether there are changes in the width of transfer effects. I think that's a really interesting question, especially vis-a-vis some theories of cognitive development and brain development. And importantly, I hope, and also with some sort of good analytic leverage, the sample might be large enough to actually say something about the absence of training effects. So that takes me to the end, and I just want to summarize. Cognitive control, I hope that I've managed to convince you that cognitive control is deployed across goal contexts, and the way this deployment happens is increasingly optimized. And as a function of environmental exposure, and it's subject to sort of cognitive training or environmental exposure can have an impact on cognitive control. The next steps in terms of the research agenda is to study the extent of transfer and to potentially identify sensitive periods in cognitive control plasticity. And sort of one of the challenges that we try to grapple with is how we can really sort of reliably capture goal development, and what that means for the way that we approach this empirically. So with that, I'd like to conclude and thank everyone in my lovely developmental change plasticity lab. This was us before COVID. This is us now, much like everyone else. These are my funders that I would like to thank, and I'd like to thank you for your attention.
Thank you, Nico. That was super interesting. Yeah, brilliant. Okay, so does anyone have any questions? You can write them in the chat, or just ask them, just shout out. I can't actually, I probably can see you actually if you put up your hand. Nico, perhaps you could stop sharing your screen.
Oh yeah, sorry, hang on. Do this. There you go. Stop sharing.
Okay, so anyone have their hand up, but you can use your real hand or virtual hand, I think. I don't know if you can, or just put a question in the chat. Gabe.
Oh.
Hey, did you call me, Sarah?
I did. I thought you put your hand up.
I did. I just didn't hear what you said. Hey, Nico, it's nice to see you.
Hi, Gabe. Good to see you too.
Good to see you well. Thanks for the great talk.
Thank you.
As usual. So I had one question, because I've also been confronted, having passed to developmental science a bit more from my economics studies. I've also dealt with this problem of how to incentivize participants, right? Because you want to see developmental differences, but then you're burdened with the question of how to incentivize them equally. And your studies now nicely show that there are some differences in the evaluation of money, for instance. And if one, is doing behavioral economics or economic research developmentally, and you would, what do you think could be done about this if there are these? So should we just do away with money? Is one question. Or have you thought about the real effort option? Seems like a good one. I liked how you put that together, but I don't know, like what would you say to the economists that are still using money in these types of developmental studies?
Yeah, I think that's a good question, Gabe. I mean, I don't think there's an easy answer, to be honest. I think it's going to be a matter of just triangulating across these different approaches. And I'm not, I mean, I guess in the context of the talk, I might sound a little bit more, sort of severe and say, oh no, we must leave that agenda behind. I think there's some real merits to it, and this has obviously been very crucial in terms of how it's been very helpful in terms of how we understand development. But I think we need another perspective there also, and I think it's just probably more about the careful groundwork, to be honest. I mean, there are good paradigms where we can just sort of, I just don't think it's enough to assume that it's the same for all populations. And I think there are ways to empirically test of whether it is or not. And I think that can easily be incorporated in an empirical context. And, so it might just be, I think the same way that we run questionnaires to check whether participants have understood a particular paradigm, that we also run a paradigm where we check, well, do they actually care enough about it? And if they don't, that we sort of manage to reliably control for it. I mean, economists work, they're all about the, controlling by means of another variable. So, I think it's just more about capturing that variance and being able to use that to explain what's going on. So, yeah, just sort of potentially including it in the actual empirical framework of investigation. I mean, I guess that's sort of a more immediate strategy. I think in the long term, I think this is sort of something that Annette Kamenoff-Smith has said, for entire scientific life, is that we need to embrace complexity, and we need to embrace complexity in the way that these developmental processes interact, but also I think in the appreciation that the developing organism is different, and that these differences are taken into account. So ultimately, I probably would like to sort of draw up a research agenda where we just get a much better handle of what tickles children and adolescents, and to sort of manage to equate that by using different rewards for different populations, but to be sure that it tickles each in the same way.
Yeah, that's a challenge. Okay, that's a great answer. Thank you.
It's Maxie from Amsterdam. It's so cool.
Hi, Maxie.
Actually from Leiden. Hi, Nico. Really good to see you.
Hi, good to see you too.
Thank you a lot for your talk. Really interesting. I have a question with regards to your model-based, model-free Decker paper or like study. I thought it was really interesting that you adapted that task design, but I was wondering how much of model-basedness you really capture with that modification, because by making it deterministic and leaving out the probabilistic structure of it that actually is replicated in a bunch of developmental samples now, is making me wonder what really is model-basedness in that sense of, like, if individuals engage in that task, where you not really have to decide between like switching and like making use of a model that you develop throughout that task structure.
Yeah, no, that's a really good question. And I think this is something that reviewers have asked us, are there sort of, really neat behavioral proxies in terms of whether model-based behavior is actually present in terms of, switching or staying after common and rare transitions. I mean, I think that task, even though it's not probabilistic, it still requires you to make an inference from one state to another state. And if you make that generalize, I mean, ultimately, model-based decision making, it's nothing more than just being able to generalize to a different state. And if you look at that task, sort of from that first state is, you've got 4 different structures, and so you've got state A and state B with 2 different rocket types. And the question is whether you generalize from one rocket to the next rocket in a different state. So I think in that sense, I think it actually manages to capture model-based decision-making very well. I think this is not just something that we see in the computational modeling, but also when we use a logistic regression in terms of the kind of rewards that are expected, the prediction errors, and the kind of choices that children make, or adults, we see proxies of model-based decision-making. So yeah, I'd be pretty confident that we're getting it.
Thank you. Okay, thanks, Nico.
So there's a question from Deborah Talmy in the chat, which I'm going to read to you. So she says, children care differently about monetary reward, but do they show different, just noticeable differences for reward?
So what does that mean? What's it?
Sorry. I'll just come in with voice. Sorry, I can't do video because I'm cooking dinner and childcare at the same time. But I listened to your talk. It's an excellent talk. The question is, do they show differences in the reward intervals that they would notice? So they might care less or differently about £2, but do they care the same about the difference, say, between £2 and £3?
Yeah. That's a really good question. Thank you. That's a great question. This is something that I left out actually in the description of the design. So we have in the cognitive control task, we have them playing for sort of a low amount and a high amount, or just relatively speaking, and we actually see a really nice difference in the effect. So the high amounts have a sort of more invigorating effect than the low amounts, for instance. So that's within a given reward. So that does suggest that it's relatively fine-grained, at least in terms of how they perceive and how they respond to it. Does that make sense? Yeah. Okay.
Sorry. Yeah, of course, it does make sense. I understand that they would be sensitive to the difference between high and low reward. But what I wanted to ask is if you have any evidence that say the difference, say, okay, in that comparison of high and low, was that comparison different in children and adults or across ages?
Yeah. Yeah, that's a great question. I mean, there have been some proposals that it would be, but we didn't find that. We actually didn't find that. So I guess what you're getting at is whether they're sort of operating on a similar scale, as it were.
Exactly.
Yeah, and they appear to be, at least in the context of this particular task. Yeah.
So we might not be able to set the same low amount, but we could increase the amount in the same level of interval, and that might give us some handle on how to motivate participants across groups.
Yeah.
Thank you.
Thank you.
Are there any other questions? I think it's getting late and people are having to leave, but I have a couple of questions. So I also think that it's such a big problem in developmental research, but not just in developmental research, in all research, the different value of reward, the different value of, but it's not just money, the different value of, I don't know, task demand rewards, how seriously you take, coming into a lab and doing a task for some random scientist. Other kinds of rewards, intrinsic motivation. I think motivation is so difficult to compare across the lifespan, especially with children, the age of children that you're testing, it's not really them who's going to be motivating them, it's their parents, I imagine.
Yeah.
They're not going to be like, oh, I'm going to train on this brilliant training paradigm. It's their parents who are going to remind them, or their teachers. And then that's in adolescence where suddenly they become much more autonomous and their motivations completely change. And then it changes back again in adult. And that is so difficult it's such an intangible thing to measure, to try to measure.
Yeah.
Intrinsic motivation. So
one sort of feels there's no way around it almost, no, because it just sort of, it affects, it just affects the core measurement process, doesn't it? When we're looking at how stuff changes and when we're trying to understand differences, and it's, I think, I guess those changes are always going to be gradual somehow, but it just seems to me, I mean, I notice it in my emotional response somehow when I listen to talks and hear people talk, sort of say that children can or can't do something. I think it's just sort of more that word can or cannot. It's just sort of always focused around these competencies without, just sort of taking into account these huge amount of influencing variables that you've just mentioned. Yeah, it's a can of worms, isn't it?
And then I had a second question. I think my internet is a bit unstable, but if you can hear me. So this is a very strange question, but training studies, training inhibition, I mean, we all know that, self-control and self-regulation is a very useful process to have and has positive seems to be associated with positive outcomes later in life. But then on the other hand, inhibition is also associated with stopping yourself taking risks. And imagine a population where no one took any risks at all. I mean, risk taking is such an important part of development and exploration of your environment and learning and succeeding in life, socially, professionally, in every way. I don't know, I sometimes wonder whether training, especially from an adult point of view, I suppose what I'm getting at is there are certain processes that are developing, presumably for adaptive reasons. They haven't developed adult levels of inhibition and adult levels of being able to suppress risk taking, for example, for a reason. Should the aim be to make everyone perfect at inhibition?
I love this question. Thank you so much. I think it's brilliant and really, really important just to reflect on that. And I remember, like, when I first wrote this grant, I was in the Netherlands and I submitted it to the sort of Dutch research organization as well. I didn't get it there, but I remember submitting it at the time and thinking, God, what are the Dutch people going to think? Here's a German that wants to just train inhibition and uber control, and like, they're just, this, I don't know, just sort of, I was a bit worried about the national stereotype that this would reinforce. But I think this is a great question, because I think, to me, what should accompany this, and in fact we sort of implement something in the context of our training, it's not just about that sort of core ability to inhibit, but also that sort of meta cognitive process of when it makes sense and when it doesn't make sense, which is, I think, what you're getting at. And it's just sort of not necessarily the blanket extension of inhibition across all contexts, but sort of, where does this make a lot of sense, i.e. in the because an exam is coming up, or sort of letting loose is fine because there might be some more time, or it's just the weekend, and what we actually implement in the context of our training at a later time point. So I think they sort of need to have done a third, and then what we start doing is we change the number of inhibition trials, and where we see whether they sort of whether they respond to it effectively, whether they learn that in that particular context. Like, I think we have a game where it switches from day to night, and night they need more inhibition than during the day. And we're interested in whether they actually update this, whether they sort of, blanket apply this inhibition to all contexts, or whether they're actually updated, and whether that sort of metric of how well they updated actually also explains things. So I think that's a really great question. And, I hope that we might even have some data to speak to. But I absolutely agree, like, it needs to go hand in hand with sort of a sensible approach, that this is not a sort of blanket remedy for everything. I totally agree.
Thanks, Nico. Does anyone have a final question?
I don't know if it's a final. Hopefully it won't be long, and maybe someone else who hasn't built up the confidence to ask the final question will. So excellent sort of warming up by Sarah Jane. I wanted to ask you about strategy, and I was going to try to limit the idea of which kind of strategy adults and kids apply, for example, for something that allegedly is well controlled, like the SSRT, and there's like brutal aspect of withholding the thing, and even in a task that allegedly is well controlled.
Yeah.
But she primed you to even ask. It's not about inhibitor control. It's actually about risk management, or in fact developing strategies, right?
Yeah.
To cope with stuff. So how is that sort of goes into the large study, where you will be able to capture whether the kids are using maybe some type of strategy during the learning, or is that something that it's in
Do you mean a strategy in the context of the SSRT? Or
no, that was an example, but in any task you apply strategy, but especially if you're doing these long studies, people start to change the way they think about how to sort out stuff.
Yeah.
And you're using always the same measure, which is right. But is there any other way we can capture what if they are changing the strategy?
Yeah.
Explicitly, implicitly?
Yeah. Yeah, I think it's a fantastic question, and you know, again, I think also in the context of cognitive control development, that really is something that you know has been noted, that the kind of strategies that that children use, or you know, sort of with age, that it changes in terms of how particular solutions are found to overcome problems. I think, like, sadly, our training study is not that suited somehow, at least not in the context of the wider functions that we look at, because it's so broad, I think, you know, and I think, you know, that's obviously a nice thing to have lots of different measures because we can answer particular questions, but it's difficult to then get them to think and reflect explicitly about strategies the entire time on any of those given tasks. I also think, yeah, you know, it's sort of, as soon as you ask someone about why they did something a certain way, it's sort of, I think in a longitudinal context, that's always a little bit dangerous too, because you might predispose them. Then, like, you know, you've made them aware of how they might be doing it, and then it could potentially change how they would subsequently do it. But it's yeah, it's sorry, it's not a very satisfactory answer, because I do think this is a really fascinating question. I don't think we'll have data on that though, but we really should.
I truly hope that by the modeling of some of these sort of multivariate, you know, latent aspect, there will be something that will allow you to capture what you think are common or specific cognitive strategies that some people apply, because that's one of the powers of those large studies, right? You get the variability and you get the latent, you know, and you might even have, you know, not even the detail, the pre-registration, but, you know, there might be something there to capture some of these slightly more ecological or real life, you know, strategies that the kids or people use.
Yeah, exactly.
Thanks for a great talk.
Thank you.
Any more questions before we go, now that it's 6 p.m? Okay, well, thanks, Nico. That was absolutely brilliant. Thanks for dedicating your Friday evening.
Absolute pleasure. Thank you so much again for the invitation. It's really, really lovely. Very, very warm welcome. Thank you.
Research, and well done for like continuing it post-COVID and taking advantage in a way of the data you've already collected to look at the impact of the training on outcomes. COVID.
Yeah. Well, let's hope it's of some use.
Yeah.
All right.
Bye,
Take
everyone.
care. Bye-bye. Have a lovely weekend, everyone. Bye-bye.
You too.